Hi, this is Robin, and in this video we'll be going over the pre-check questions for discussion 11, virtual memory. Before we get started, let's have an overview of what virtual memory is. Virtual memory gives each process the illusion of having its own large memory, and it maps our virtual memory space to physical memory. Since virtual memory is often bigger, whatever doesn't fit in our physical memory or our RAM or main memory is stored on the disk. So both our virtual memory and physical memory are divided into pages of all the same size, and the pages of the virtual memory are equal to the size of the pages of physical memory. So we can divide our virtual address and physical address into page number and offset. So how do we map our virtual memory space to our physical memory? We have something called the page table, which holds the mapping from our virtual page numbers, or VPNs, to physical page numbers, or PPNs. And then to translate from virtual address to physical address, we look at the page table for the VPN to PPN mapping, and then we append the offset to the end. So as an example, here's a virtual address that we split into our VPN and offset. We look in our page table for the mapping between the VPN and PPN, so the page table outputs the physical page number. And then we append the offset in our virtual address to our physical page number to create the physical address. This works because the virtual pages are the same size as our physical pages. So the number of bits to represent the offset are the same between the virtual address and the physical address. From here, we can use this physical address then to look for our data in our cache or our main memory. However, if the page table does not contain a valid mapping from the VPN to a PPN, then we have to fetch the page from disk and load it into memory and update the page table entry with the updated mapping. And this is called a page fault when there is no valid mapping. So the page table is located in main memory since it's a lot of information to store. However, because of this, multiple memory access are required for each data access, which can take a lot of time. So the solution is to have a cache for our page table, and this is called the translation look-aside buffer, or the TLB. It essentially stores the recently accessed VPN to PPN mappings. It is important to note that this only contains the mappings, it doesn't contain the actual data. So here is the general flow of how we go from a virtual address into getting the data for our process. So first of all, we split our virtual address into the VPN and offset. Then we check the TLB for the VPN to PPN mapping. If it is a TLB miss, then we have to check the page table in our memory. And if this also does not have a valid mapping, then we have a page fault. And we must fetch the page from the disk, store it into memory, and update our page table with the proper entry. Once this is finished, we can go and load our page table entry into our TLB, translate our virtual address to our physical address using the mapping, and then now that we have our physical address, we can check our cache whether it has the proper data block, and if it doesn't, we get the data from memory, store it into the cache, and then finally we can return our data to the process that requested it. Now we can move on to the true-false questions of this discussion. So the first one states that if a page table entry cannot be found in the TLB, then a page fault has occurred. So remember that the TLB serves as a cache for the page table, and a page fault is when the page table itself misses, and we have to load the proper page from the disk. So it is entirely possible for the TLB to miss, but for the page table to have a valid mapping. Therefore, this statement is false. The page fault occurs either when a page cannot be found in the page table or if it has an invalid bit. The second question states that the virtual and physical page number must be the same size. So this is referring to the number of bits to represent the VPNs and PPNs. So if you remember, we stated that the page the pages themselves must be the same size. However, virtual memory is often bigger than physical memory. Therefore, it is entirely possible for virtual memory to have more pages than physical memory. Therefore, this statement is false. There could be less physical pages than virtual pages. However, the page size does need to be the same between the two. And this concludes the pre-check questions for the virtual memory discussion.